So let me continue on this proof of epsilon regularity theorem. I just finished the first part. So what I just accomplished, or at least gave you some idea of the proof, was to get this estimate that under the assumptions that I stated before, what I had is this difference. So this is like unit disk area, and this is the amount of area you have in the cylinder with unit radius. And as I explained to you, this is like Dirichlet energy of the graph, if it's really a graph, okay? And that's bounded in terms of this L2. But in fact, I didn't quite state this very clearly, but I will somehow supplement this information that this is bounded by some constant times the supremum over all time interval, taking the sort of soup of this quantity, L2. Okay? And in fact, even though I don't really go into this much of, well, I don't really want to go so much in detail, but actually, if this turns out to be, this can be bounded by constant times L square, where L is the one that I defined before. That's the L2 space-time integral. Okay, so maybe I don't really explain this part. It's a bit. I probably prefer to do some other things. And the other thing is, once you get this one, because the variation of this quantity is basically controlled by this h square, or from Brakke's inequality, you get this mean curvature L2 space-time integral in terms of this same quantity, which is bounded by, again, constant times L square. Okay, okay, so just to compare with the time-independent situation, let me actually tell you how you can get this in case that just a varifold is stationary. Okay, just a stationary varifold case. Okay, just as a comparison. Okay, so notice that what this means is okay. So I need to have some vector field fed into this one. Okay, so this was the stationary condition, G1 compact. Well, let's say again the same thing. Rn. So suppose B is just stationary, so mean curvature 0. Okay. Notice that this is equal to h dot, well, minus h dot g dv. Okay, so that's okay. So in this case, yeah. Okay. Anyway, so this means that h is equal to 0. Anyway, so in this case, what do you get? I mean, how do you get the same things? Actually, it's very easy. So all you can do is, you just let G, you just choose G to be the following. Okay, G is phi t x times t perp x. Okay, just feed this vector field into this first variation formula. Okay. Then what you have is that, well, remember the definition of this first variation. Also, this is by definition is a trace of S composed with nabla G of X of dv xs. Okay, so that was the definition of the first variation, right? Now, if you look at the nabla G, well, you have, by the way, sorry, this is square. Yeah. So if you differentiate this, you get the 2 phi t nabla phi. Okay, let's see, with t perp of x. And differentiating this one, you get phi t square. And actually, if you differentiate this, it's just all you get is actually this matrix T perp. Okay, that's an n by n matrix. That's tensor. Okay, so this is n vector tensor n vector. Fine. Now you plug this in, and we know this is 0. And then what you get is this is where this derivative term, which is, oh, sorry, let's see. Oh, yeah, that's OK. Where you get the two trace of S composed with 2 phi, number of phi, T perp of X, and plus this this one. OK, maybe I just separate already. And trace of S, and well, phi t squared is a function, so let me put this outside. OK, so that's what you get. Fine. And then you move this on the other side, do Cauchy-Schwarz. OK, you do usual Cauchy-Schwarz, and you can actually kind of, well, by Cauchy-Schwarz, I just skip this part, Cauchy-Schwarz. You can actually prove that a trace of S T, this one, is, well, less than or equal to constant times, well, with a little bit of computation, you can show that this is less than number of phi t and T perp of X squared. Okay, something like this, okay, by doing Cauchy-Schwarz. And I notice that what this is, okay, just to give you the feeling of this, let's assume that, well, k is n minus 1, okay? And suppose that it's already a graph, okay? Just to give you what this is. So if suppose that the support is already is a graph of f, then you remember that, okay, sorry, you have, of course, this one. This is what? This is actually, S in this case is the projection to the tangent space, and of which you can write this as I minus nu tensor nu, where nu is the usual, unit normal to the graph, which is like 1 plus number of phi square and minus number of phi 1. Okay. So that's the projection to the tangent space, and remember T perp in this case is just well, okay. In this situation, T perp is just what is a matrix? This is just a 0, 0, 0, and only 1. Okay, that's T perp, because there's only one direction, right? This way. So the T perp is just this one. And then notice that S T perp is, well, it's just the last component that you have to look at. And the trace of this, you can actually check that this comes out to be 1 minus, I think 1 minus, let's see. You just take the last component. So let's see, what's the last component? 1, yeah, that's right. 1 coming from the identity minus, I guess, let's see, nu, the last component is nu n, nu n. So yeah, 1 plus number of f square and 1, I guess, yeah. Right, okay, so that's what you get. And which is actually this one. And if number of phi is sort of small, this is, again, number of f squared. Okay, so that is an estimate, like Dirichlet energy. And notice that the right-hand side is like L2. Okay, so in the case of this time-independent case, it's just plugging in this function. You get this estimate, actually, more or less. Okay, so if you are working with this sort of static case, getting this estimate is as simple as this, more or less. I mean, I'm exaggerating a little bit. There's just something that you have to do, but more or less that's what you get. But with this Brakke setting, there are a lot of things you have to do to get this, first of all. Now, once you get this, and there's another ingredient I'd like to show you, which is the so-called Huskins monotonicity formula. And I don't really have time to present the full usage of this, but just as since this is an important part of this proof, I just show you how this can be true, monotonicity. Yes?
So in the case, so what you said, if the V that you have over there were stationary, I mean, we're independent of time,
Mm-hmm.
you're really saying that you can get this density, the oscillation of the density bounded simply by the
L2, yeah.
distance?
Yeah.
And the same thing for H, so that's what you were saying.
Well, H is 0 in something, right, in a static case. Yeah, so the second one is trivial in some sense for static case.
This is the case with H. H is your velocity.
Yeah. Right. Velocity, yeah. So in static case, the second you don't need it actually. It's just 0. So, but here, you have to estimate. Yeah. So it's a very different picture. You get studying Brakke flow somehow. It's something you don't think about in case it's static. Yeah. So.
But you have this estimate in the case of static.
Yeah, you do. Yeah. It's just that some of these things become trivial. But first line is not, I don't think. Yeah. Right. Okay, so parabolic monotonicity formula is this is so-called Huskins monotonicity formula. So this is very important I can't really explain this in full detail, but this is important when you try to construct Lipschitz approximation. In fact, that's where you use this. But so let me show you the proposition. So now, I just want to show you this formula. So for the moment, let me assume that actually we are looking at BT, which is let's see. Well, actually, it doesn't have to be even unit density at all. It's just a Brakke's mean curvature flow. And just for simplicity, here only let U to be, say, Rn, and it's a Brakke mean curvature flow on the entire Rn for some time interval. And then the following is true. So this is very interesting. So let rho of y s. So you have you have a 4. Okay, so y and x are in Rn, and s is bigger than t. Okay. So this is, you define this as a so-called backward heat kernel of k over 2 e to the minus x minus y square for s minus t. Okay, so this is something I'm sure you've seen. It's a heat kernel. But notice this is, you see, this is defined on Rn, but this is a heat kernel of k-dimensional nature. Here you see you have k. Okay, so this is k-dimensional, even though it's defined on Rn. Okay, so that's somewhat different. And then my claim here is okay, so I'm having this Rn. Okay, in case it's a bounded, if you want to use it for bounded domain, you can actually do some sort of suitable cutoff function type of things. But here, I don't have to worry about it. And what you can prove is this quantity, if you integrate, okay, no, maybe. So important thing is you fix ys, okay? And think this function as a function of here x and t. Now, so you are integrating with respect to x here, okay? So you are integrating with respect to this variable x, and think this as a function of t, and differentiate this t, okay? You see, notice, again, I want to emphasize, you are integrating with respect to this x, with this measure, okay, you are integrating. And t is, y and s, you just fix it. You fix and don't move it, okay? And t is the variable here. Then this quantity is less than or equal to 0. So that means it's monotone decreasing in time, okay? Now, I have to actually interpret this in the sort of integral expression, but let's just use this differential formulation. Just it's easier to write this way. Okay, so let's check this proof. Basically, all you do is, well, all we can do is really plug into the Brakke formula. So now, so let's see. So the Brakke's inequality tells you that this, this rho. Well, let me write just as rho. Okay, let me write this as just a rho for simplicity. Okay. Now, this one, by Brakke's formula, number 5, okay, the condition number 5, this is less than or equal to, again, I emphasize that this, you should write this in an integral form, but I'm just skipping that part and pretending like it's differentiable, okay? So this is less than or equal to, Rn. First, you differentiate this with respect to time, and then you have this nabla rho. Here, everything is with respect to x minus rho h dot h. Okay, that's formula you have to have, and then what you do is the following. So this is equal to d rho dt. Now, so we have first of all this rho h squared term, okay? That comes from this one, and you have this product. But now you do these little things of instead of just keeping nabla rho dot h, I take 2 here and then subtract the same thing, okay? And okay, so that's it. Yeah. Let's see. I guess we have that. Okay, that's fine. Yeah. dvt. Okay, that's fine. And now, one thing that we have to have here is that, I do use the perpendicularity of this mean curvature vector, and since I know this guy is normal to the tangent space, I can take a normal component. Okay, so this means you're taking only the normal component of the with respect to tangent space of this guy. Okay, so it doesn't hurt to do this, and then you add and subtract the same quantity. Let's see. I think that's correct. Over rho minus this quantity. Okay, we do this. Now that can be, you can complete the square of this one. Okay. Let's see, you have minus, so maybe this guy. Okay. You can complete these things as minus rho h minus, I think, rho nabla rho perp square. Okay, you can check that this comes out to be these things that's circled. Okay, this h square term here, this product term end up being this one, and the square of this guy times rho comes out to be this one. Okay, you can check this. Correct. So that's a negative term. So you can drop it, and then you end up having this 0 dt. And let's see, plus the other things you do is now this one, you see this is like the first variation formula. This is, this is h dot vector field. Okay? So you can use the first variation formula or the, the one that I just used there, for example. That's what I mean there. So that you can actually write that as a trace of s second derivative of rho. That's equal plus rho over Nabla rho perp square. Okay. Well, let's see. Now we have s, so maybe I should keep this b of txs. Okay. It's okay. You see, I use the formula that, well, maybe I should say that then Nabla rho dot h is equal to minus of first variation of this rho, which by definition this is really is equal to trace of s composes second derivative of rho. Okay, that's what we have here. And so finally, it's a sort of a miracle that for backward heat kernel, in fact, this quantity is always 0. It's somehow a miraculous formula that you have. This turned out to be equal to 0. That's something you can check that you see. Okay, so why is that so? This, you see, this is a 0 dt plus trace of s Nabla square rho. And now this perp is nothing but, in fact, rho over, well, identity minus s Nabla rho square. Okay, and a little bit of computation tells you actually this for any s. Okay, well, for any s in G and K, this is equal to 0, in fact. That's something that one can check relatively easily. Okay.
The K in the heat kernel should match.
Yeah, exactly. Yeah. That's just that's true only for the same index K. Yeah, it's actually a little bit of computation you can check. Well, you can, say, for example, assume that S is, it's everything is isotropic, so you can assume S to be 1 and 0, where this part is, K, and this part is N minus K. You can check with this, projection, compute this, you see it's 0, in fact. Yeah. Okay, so this gives you. That's it. Oh, okay, this is it. So this says that this is less than or equal to 0, and you get this formula. Okay, and this is very useful. I wouldn't want to go into this detail, and maybe so these are some of the ingredients, very sort of special ingredients, and then okay, maybe I stop around here about this one. So the rest is again somewhat, well, there are a lot of sort of technicality you have to carry through. And I just say a few keywords. And then I'd like to also mention that there are a lot of things that to be studied still. This is really still the beginning, I think, of the Brakke's mean curvature flow. And so maybe the next step is to, okay, just a very outline is that the next is you construct the so-called parabolic Lipschitz approximation of the support of Bt. So this step is the same as sort of elliptic case too. In the Allen regularity theory, which is an elliptic version of this, you also construct a Lipschitz approximation of this graph. But here, Lipschitz in parabolic sense. So meaning, you see you have a natural distance when you're studying a parabolic problem, and with respect to the metric, you construct Lipschitz approximation. And here, the Hugheskin's monotonicity formula is actually quite essential. Unless you have that, I don't think it's possible to do that. Okay, and then after that, you do sort of a blow-up argument. Okay, so for the people who knows about this, you may have some idea, but I don't really want to go into this. So blow-up argument. And then, well, you have a sort of sequence of varifold, and with this corresponding L, let me call this Li, going to 0. So that's a sort of standard trick. You consider a sequence of Brakke flow whose L, which I call Li, goes to 0. And then so let Fi to be a Lipschitz approximation that you constructed this. And then you kind of rescale this by this Li. Let's call this F tilde I. So I'm sorry, this probably doesn't make sense to many of you. But just for people who know about this kind of thing, let me just quickly say that so Lipschitz approximation you construct, and then you normalize it by this L2 norm in some sense. And then you show that this guy Fi converges to some function f, and you show that this is actually the solution of the heat equation. Okay. Yeah. Yeah. Li is the you remember L? L is the L is in the previous. Oh yeah. Well, in the previous lecture, I wrote the expression for L. L is a sort of a space-time L2 norm or distance square integral.
So you just integrate that heap of square integral over the time again. That's the L.
Well, yeah, that's right. If you integrate that guy with respect to time, that's your L. Yeah. But anyway, so you show that the limit is the solution of the heat equation. In an elliptic case, this becomes a harmonic function. But here, it's naturally heat equation. Okay, and the heat equation has a nice estimate, and you use that to show so-called the decay estimate, and then that's how it goes. So the rest is philosophically similar to elliptic situation, and but I think the biggest stark difference should be this first step. So this is a place I wanted to explain. Okay, and finally about this epsilon regularity theory. So let me finish at this point. It's very sketchy, but I hope that you got some feeling about this. Now, I just want to mention that this is really still almost like first step of the analysis of this Brakke's mean curvature flow. So something I like to mention is 4.5. Just something I like to mention is the I skipped the whole thing, so 4.3 maybe. So further remark is that so far not much is known about the singular set. The one that I mentioned, that's CT, singular set. About the singular set, very little is known, except for the dimension 1. I would say when k equal to 1, okay, a lot of unknown. except for k equal to 1 case. I have recently joint work with Vikram Sekera is having some estimate of the one-dimensional triple junction case. We have some kind of efficient regularity theory for this one. But that's pretty much the only result, I think, as far as I know. Okay, so in some sense, building upon this work, hopefully there will be a development. The other things I should mention is that there's a notion of so-called tangent flow, which corresponds to more or less to so-called tangent cone in a minimal surface case. Okay. So in a minimal surface case, there is so-called tangent cone, which you get like the one that Diana is doing. Somehow you do the blow up, and then you get some kind of homogeneous object called tangent cone. And for Brakke's flow also, actually, there's some kind of you do a parabolic blow up, and then you get some cone-like object. There is some subtle difference. That is, this is a guy who is homogeneous only backward in time, somehow not forward in time. It's kind of strange, but it's cone only in sort of backwards in time. Really, just I don't know how to explain more than that. So there's a sort of interesting difference from minimal surface, but there's some analogy. So there's, I think, a lot of things you can actually look for. Since there has been so much work on the minimal surface, there are a lot of things that you can try to imitate, first of all, and maybe you probably see some difference or certain new things. And I hope that this is going to shed some light to even a minimal surface theory. Okay, so that's the end of the Brakke's Curvature law. And now I'd like to move on to the second topic. Did I start at 4? I guess I started at 4, right? Yeah, okay, so that's doing well. Okay, so now this is the end of the Brakke flow. Okay, so next, it's totally new subject, even though it's very much related. That's the so-called Modica-Mortola functional. And Giovanni, I think, is going to talk a little bit about this too. But first, okay, so that's new things. So 5, Modica-Mortola. And depending on the people you talk to, this Modica-Mortola function could be Allen-Cahn or Ginsburg-Landau. I'm very confused about this. Which is the right one? Ginsburg-Landau, and also I guess let's see, Van der Waals, Cahn-Hillier. So okay, so there are many names of this. So, but it can, well, mathematics is the same, just the name is different. So let U is let omega be a bounded domain Rn. Okay, so well, it could be the whole. Okay, so maybe I shouldn't say that it's bounded. So omega is a domain, and U is a function. It's a scalar function. Okay, so and epsilon is a parameter which is very small, typically. And then you consider the following functional, which is extremely interesting and very rich, I would say, in structure. So consider the following functional. Let me write this E epsilon of U, defined as the integral of this quantity epsilon times W square divided by 2 plus W of U. Okay, and integrate. Where this W of U is so-called double well potential, So the typical one is 1 minus u square over 2. But it could be something which is of the same nature. So this w is the one that has 2 minima, 0, and 1 maxima, typically, like that. Okay. Non-convex, that's very important. Okay. If it's convex, you don't have this kind of situation. So this is sort of this. I think that's the simplest non-convex problem of scalar function, and very interesting. And now notice that this functional is with no other constraint. Obviously, when u is equal to -1, constant, energy is 0, of course. And when it's +1, constant, this is 0, 0, so that's 0. So obvious absolute minimizer is just constant -1 and +1. Okay, that's easy to see. But the things that we like to consider is that's a situation where you have a mixture of the plus and -1. Okay, and by the way, so this comes from a model of phase separation. And it's been used a lot in the numerical simulation of, say, material science, particularly about the alloy, of the time evolution of alloy, for example. And I'm always very impressed that this has been used so much in numerics. To describe how the so when I say phase, meaning there's so here's omega, and typically, well, I'm going to explain this, but so to have sort of order 1 energy, okay, when so here epsilon is very, very, very small, and actually I want epsilon to go to 0 in some sense, and when it's very, very small, you see you have this term which really penalize this quantity unless u is 1 or -1, of course, right? If it's, say, here, I mean, you are dividing by epsilon, so this gets extremely large as epsilon goes 0. Now, okay, well, so in some sense, order 1 configuration of this energy is the one that you have the region which is mostly +1 and mostly -1, and there is well, here it's probably not clear yet, but there's sort of thin layers of phase transition from -1 to +1. Okay, so I'll explain what this is. So there's this kind of hypersurface-like region where the transition from +1 and -1 occur. Okay. So, but just to get you some pictures of this, let's first consider the one-dimensional situation. So that's very explicit. So let me explain this. Okay, so this is just it's a beginning. So let's consider the 1D case. Okay, just to start. Now, for 1D, let's consider the simplest situation where omega is just a real line. Okay. And as I said, you have obvious minimizer +1 and -1 with energy 0. That's of course not interesting. So let's just force this to be non-trivial, and let's consider the configuration where at -infinity it's say -1, and +infinity is +1. Okay. So let's see what this is. Okay. So you see, just to make this thing non-trivial. Okay, now under this condition at infinity, let's minimize this energy. Okay. Well, the existence of minimizer, well, you can actually show, and let's minimize E epsilon under this condition. Okay, now existence of minimizer is easy, but now then, okay, so there exists such minimizer now, and Euler-Lagrange equation. Well, of this energy, well, in this case, it's just epsilon u prime square over 2 plus w of u epsilon dx. Well, I think everybody can do this. Euler-Lagrange equation, it's very easy. And you see, you get okay, so you get the first term gives you the second derivative term. So you get Euler-Lagrange equation minus epsilon u double prime plus w prime of u over epsilon equal to 0. Okay, I think no question here. Fine, yeah. So that's the equation that should be satisfied by the minimizer. And it's actually interesting that this is completely solvable by multiply a little bit of calculus, multiply this equation by u prime. Okay, so that you get minus u double prime plus double prime of u prime of epsilon equal to 0. Then you notice that this is actually the derivative of this one, 1/2 1 over epsilon u prime square plus w u over epsilon of prime is equal to 0. You see this, right? Because if you differentiate this, you get 2 comes out u prime u double prime. This is double prime u prime. Okay. And so this is true. Then this has to be constant, of course. Okay. So this constant now this guy is constant. And also, well, what is the constant? Well, if you think about the condition at the infinity, it's supposed to approach to +1. So it's supposed to be approaching to some constant. So well, from that you can kind of guess that this constant has to be equal to 0, in fact. So u prime square plus wu over epsilon is actually 0. Okay. Because at infinity, w has to be 0, and the u prime, of course, has to approach to 0. Right? Okay. Minus. Okay, sorry. Yeah. Okay. Yeah. Where did I? Okay, maybe I'll just stick minus here. Okay, thank you. Yep. Fine. Okay, so now, all right. So that's very simple, but very instructive, in fact. Now, so 1D case is completely solvable. You can do furthermore the, well, okay, you move this guy and then take a square root. And assuming that u prime is positive, which is kind of assume, well, okay, so let's assume this one. Then you have, let's see what you have. Yeah, epsilon w u prime is equal to square root of 2w of u, right? That by just moving that and then taking a square root. Is that right? Huh? That's fine, yeah? Yeah, epsilon square here and then take a square root, yeah? So you get that. And this can be solved, in fact. The solution of this first order ODE is u of x is equal to, this is hyperbolic tangent of x. And actually there's a freedom of this translation. Okay, so that's actually, yeah, using the fact that the w is explicit function given by, okay, so in case w is equal to 1 minus u square over square p, then you can actually solve it. And that's a solution, in fact, hyperbolic tangent. Okay. So the minimizer is one which is, okay, let's say the c equals 0. Okay, that's centered at 0. Then, well, this is a very nice function which approaches to plus and minus 1, but exponentially fast. Okay, and when epsilon, so epsilon I want it to be small. So this change from minus 1 to plus 1 takes place in the distance which of the order of epsilon. Okay, if you go far away, it's exponentially close to plus 1 or minus 1. So this looks something like this. Okay, and this, I'm just saying that this order of length is epsilon order. Okay, if you say go about 10 epsilon, for example, it's extremely close to plus 1 or minus 1. Okay, so that's a profile of minimizer, and also I should say that what is the energy of this guy? So energy of this 1D profile is equal to, you can compute this explicitly because, well, what we proved is that these two terms are equal. Okay, so you have two terms, right? But they are equal. Okay, so let's see. So you can actually, okay, so maybe I should write this u prime square plus w over epsilon. You can change this to, all right, so this, you can change this to actually u prime square root of 2w dx by just observing that they are equal, and so it's actually equal to epsilon times u prime square, for example. Okay, and then you just substitute u prime by this guy. Okay, so that's the same. And then do a change of variable s equal to u of x gives you ds equal to u prime of dx. Okay, so you can actually get this. Huh? Well, epsilon is gone now. Yeah, epsilon is. You see, this one is epsilon u prime square, which is epsilon u prime times. Let's see. So u prime is this one. Epsilon over 2w. So this goes away. Okay. So this, after this change of variable, notice that this, after change of this variable, the integration of s is from minus 1 to plus 1. Okay. I think at this time of the day it's hard to follow this algebra, but hopefully I hope that's okay. At least I think this is sort of college level, so maybe I hope it's not so bad. But so this is 2s ds. Okay. So it's independent of epsilon. Finally, only depends on w. Okay. Once w is fixed, it's just constant. Okay. So let's call this as sigma, and which is very important, independent of epsilon. Okay. So this tells you to make a transition from plus 1 to minus 1, or minus 1 to plus 1, independent of epsilon, you have to pay this energy to do this transition. Okay. So now, okay, so this is usually called the surface energy constant, or surface energy density, I guess, but energy constant. Because you have to pay to make a transition from plus 1 to minus 1. And that's sort of like a surface energy. Okay? And also the other things that one noticed is that this energy is really concentrated at this interface of plus minus 1. Okay? So what I mean is that the other remark is that, very important remark, is that this energy if you think this as a measure, okay, if you think this as a measure, you see, away from this place where the transition occurs, everything is very close to exponentially, exponentially close to plus minus 1. So all these things is concentrated only around here. Okay, so let's call this. So suppose this point is C, then actually as epsilon goes to 0, this converges to actually delta function at C. Okay. So times, by the way, sigma, okay, because you see you have the weight of sigma. Okay. So as epsilon goes to 0, that's what you see in 1D case. It's really concentrated. It's a delta function with weight sigma. Okay. Now that's the 1D picture. Now, okay, so let me start. And so this is a 1D picture. It's very simple. For what we learned is that this energy, when you want to make a transition from +1 and -1, you have to at least pay this sigma energy for any epsilon. And as epsilon goes to 0, this energy is going to be a delta function. Okay, energy is concentrated. And so what I'd like to talk about is the what happens for higher dimensional case. So higher dimensional case. So now we consider the same energy, exactly the same energy. And so as I draw the picture, so once you get this 1D picture right, it's not so difficult to guess that if you have some configuration of the order, energy order epsilon, well, the same guy. So okay, so if you have order 1 energy, okay, so that's very important. I mean, you could be looking at something which is much higher energy, but I'm interested in the one which stays sort of finite as epsilon approaches 0. Then the typical kind of, I'm saying that not, with no sort of rigorous way, some typical configuration should be the one that you have a very large +1 area, and the place where it's very close to -1. And then there's, as I said before, is some kind of transition region, which if you look the sort of transversal picture here, okay, the transversal picture should be looking like 1D, like this. Okay, so +1 to -1. So I'm just saying that here, if you look how function is changing, it goes from -1 to +1 with the order of, say, epsilon, okay, making transition. And you can guess, well, if you have more of these transition layers, the energy bound to be larger, right? If you have more of this, naturally, you expect that the energy is going to be large. And so this size is like of the order epsilon, okay? And you see, so the idea is that, well, then this guy should behave like a surface energy of this boundary. You can kind of expect that. So the expectation is that the point is, well, it's very sort of very vague, but as epsilon goes to 0, this, and also if you assume that this energy stays sort of finite, okay, some say less than C, then the sort of expected is that this energy behaves like the surface energy of, is proportional. And also we know that to make a transition from +1, you have to pay sigma, and it should be, well, the sigma should be the sort of the per unit area energy of this this transition. So this should behave more like sigma times the area, surface area of this area. Okay, so that's somehow very roughly is something that you expect, at least in the first order term. Okay, of this boundary. Yeah, it's kind of here is a you see you think as epsilon goes to 0, this becomes 0. This becomes 0 thickness. So you would have this kind of hypersurface.
So you don't just say that is the level.
Yeah, you can say level set of say, yeah, maybe surface area of, I mean, very roughly speaking, u epsilon equal to 0. Say that's like the surface which lies in this there should be some hypersurface which is u epsilon equal to 0 here, and then maybe you can say that way. But yes.
So how I understand that you expect it
Yeah.
to be a measure on that interface.
Yeah.
But how do you know that that measure is going to be absolutely continuous with surface measure?
Oh,
that you
come on.
expect to have
I'm just talking about just heuristics now. Don't rush. Okay, so that's still a bit too much to ask. Okay, so I'm just saying something that you might expect to be true. Okay. I mean,
our expectations are different, and I want to understand.
all right, yeah. But let me just state. So the other things that one may expect, I mean, this may not be justified, but just for the so the other thing, just from extrapolation from a 1D situation. Okay, so if you think about this energy divided by sigma, in case 1D, this converges to delta function on this phase transition. So you kind of expect that this should converge as epsilon goes to 0 to the surface measure. Okay, so this should be like hopefully this is sort of a phase boundary in the limit. Phase boundary means it's a boundary of +1 region. Okay. So that's something that's expected. Okay, just to make the presentation simpler, let sigma be normalized to be equal to 1. Okay, because by multiplying suitable constant to W, you can always make this to be 1. So let's just sigma to be 1. So now, but this is a very simple picture, of course, and I'm not claiming this is the case under this. And if you think about it, if you really think this is like a surface area, all I'm doing here is just if you have a bounded surface area, what can you say about the limit? But we know if you just have a surface area bound, the limit could be crazy, right? I mean, we wanted to have something more than that from our experience. Yeah, at least you want to, for example, you want to have some other quantity to be bounded, such as say first variation, for example, or maybe it's minimizing and so forth. Okay, so you need something more than this, definitely. Okay, from what we know from this kind of calculus variation problem. So, so for example, one thing that it's probably better to control is the first variation. And the first variation of this energy is, just an Euler-Lagrange equation. So, if you have a control of this quantity, for example, which is the Euler-Lagrange equation, so that's the first variation of this energy. So, you kind of expect this may correspond to, if that energy is like area, the first variation should be mean curvature. Okay, so this you might expectation this may behave like mean curvature. So that's also it's a question mark, but at least something that you can kind of expect. Okay, and so that we have various wish lists. So here's a wish list. So the idea being that this should be like a surface area. Then there are a few things. Well, maybe I just state 5 things. So maybe the thing is, if you have a this energy minimizing U epsilon. Okay. Anything? Okay, fine. So suppose you have energy minimizing with some extra constraint, because if you just minimize, then you only have trivial solution. So you might want to have some extra constraint. Now with that extra constraint, which I don't specify, this minimizing guy, well, should correspond to like area minimizing. So the correspondence should be this as epsilon goes to 0, the limiting interface should be maybe area minimizing. Okay. And number 2 is, well, if it's not minimizing, but if it's just a critical point. Again, critical point with some constraint or without constraint. Maybe you wish this to be just, well, area. If you have area and if you have a critical point, that just means minimal surface. Okay? So minimal surface. Not necessarily minimizing, but just mean curvature 0. And number 3, if you go a bit further, maybe if this guy is E epsilon stable critical point. Well, stable meaning the second variation being non-negative. Okay, so then maybe it's a stable minimal surface. Okay, and this goes a bit more. Okay, and number 4 is this one comes from the experience with the varifold, but there's in some sense some kind of bounded first variation. Well, this is like mean curvature bounded situation. Well, you expect maybe something of the bounded first variation. Well, maybe I should say surface with bounded first variation. That's another kind of expectation. And 5 is that if you consider this energy gradient flow, so that's the time evolution, then in the limit you expect maybe if this is a surface energy, the time evolution of the surface energy should be mean curvature flow. Okay, so this is another expectation. And actually, they turn out to be more or less true, in fact, surprisingly, in very general setting. Okay, so the claim, I mean, I'm not saying everything, but more or less 1 to 5 are actually true in a very general sense. Okay, and okay, so I discussed this, what to do, and actually Giovanni is going to talk about. Do you have time? I wonder. You will do. Yeah. Okay. Okay. Yeah. Giovanni is going to talk about one. Actually, minimizing. Yeah. So we'll talk about this. Okay, and then I like. Well, I have a choice of. So I worked in some sense I worked all of this, and but out of these I'd like to talk about more or less 2 and 3. Okay, I like to talk about these 2 and 3, and just I quickly tell you that I kind of mentioned this already, but the gradient flow does converge to Brakke's mean curvature flow. In fact, that's one very nice result about this. That is, if you consider the parabolic gradient flow of this energy as epsilon goes to 0, the surface energy converges precisely to Brakke flow. Okay, completely generally, with any finite initial data. Yeah.
Presumable to reasonable one, not to one jumping to zero or something.
Sorry,
Can it converge to the one mean curvature flow jumping to zero?
jumping to zero means you mean the okay, non-trivial one. You mean?
Okay.
Yeah, yeah. You actually this one you get non-trivial solution. Yeah, that's actually very interesting things. Well, in some sense you have this sort of you get this result as a boundary of a domain, so you can't eliminate, interface somewhere right away. Yeah, actually that's an important point. Yeah, you get non-trivial solution as a limit of this. Yeah, right. Okay. So today, well, I have 15 more minutes. Yeah.
So you're going to obtain some sort of regularity about this boundary, this interface.
Mm-hmm.
Do you also obtain results about the domain itself? Like, for example, you look at the place where the thing is 1.
Mm-hmm.
Do you also, can you say?
Well, I don't really have any sort of characterization of the domain itself. I just, yeah, maybe not. Yeah, only interface. Well, yeah.
Maybe, I don't know if you know what it means to be non-tangentially accessible, but I'm just wondering these.
Okay, non-tangentially accessible. Okay, well, we'll talk about it. Yeah, maybe. Okay, so now first, okay, let me just make a headway just as much as I can. So number 6. So I like to talk about the number 2. That's the critical point. Okay, so this is a critical point. So this one is this one is more or less the work I did with Hutchinson, myself in 00. And so the problem, so let me just state right away what the theorem is. So theorem A. So suppose, okay, so let me state this rigorously. This epsilon I is B such that it's positive and the limit converges to 0. Okay. And suppose that the U epsilon I is a critical point of this energy. Okay. Be such that number 1, the energy is uniformly bounded, is bounded by some number, say C1. And so, as I said, this corresponds roughly the area is bounded uniformly, okay, for this sequence, area bound, roughly speaking. And number 2, also, well, this number 2 condition is not so essential, but just for avoiding technicality, I just assume that this soup is bounded by, say, some 1, well, let's say 2 or something. Well, the point is, this guy is, the place which is interesting is when U is between 1 and -1. So anything which is away from plus minus 1 is actually not so relevant. Okay, so I assume this, which is very sort of technical. Number 3 is it's a critical point, so that means the Euler-Lagrange equation is satisfied, which I might call this as okay, maybe I'll just okay, this is 0 on omega. Okay. Then what you can say is following. So what I like to say is that, in fact, what I said is correct in the sense that the limiting energy measure is actually a minimal surface in the sense of varifold. Okay, so just to state what exactly is, so let's define the following varifold, which is naturally associated with this energy, okay, as follows. This is so it's a varifold. You know, to define varifold, you need to produce some number given a compactly supported continuous function. So for any phi, which is a compactly supported function on g n minus 1 omega, you define the varifold, the integration as follows. So you define this. So, you know, given u epsilon I want to produce a very natural varifold from that. Okay, so the way you do it is the following. So you integrate the place where the gradient is non-vanishing. Now what is integrating is phi of x. Okay, so remember the phi takes two variable x and also Grassmannian. And at the Grassmannian, the most natural thing is the projection to the level set. And that's sort of, if you think about it, that's very natural, I think. So what I do is I plug in the projection to the levels, the tangent to the level set. Okay. So this times surface energy. And here is another surface energy. Okay, so that's dx. Okay, it's a bit long, but idea is that you not only look at this surface energy, okay, you also take into account this information about the tangent. Okay? And then notice that the weight measure of this varifold, is actually nothing but the surface energy. Okay, so because the way you compute the weight measure is just forgetting about this tangent, right? So this is nothing but just this energy. Okay, so note. The weight measure is just the surface energy. Maybe, yeah, sorry, I guess restricted to the place where gradient is non-zero, I guess. Okay. Now, so, and also maybe I should say that, and also the total mass is bounded by C1, okay, because you know, this is like part of the energy, and so if you integrate the whole thing, that's bounded by this C1. Okay, so it's a uniformly bounded varifold. Okay, so by the compactness of a Radon measure, there exists a subsequence which converge, and the conclusion is the following. So so take any subsequence which converge. Okay, let V be a limit of any subsequence, in fact, B epsilon J I be the limit then what one can say is that actually this guy is stationary varifold. Okay. Then conclusion is that then one is that number one is that this limit, okay, maybe I should say V0, okay, just to indicate that's the limit. Okay, so any subsequence, you know, the limit, then this guy is actually, first of all, this is integral varifold. Okay, and second, this is V0 is stationary. That is, the first variation is equal to 0, okay. Or generalized mean curvature is 0, okay, whichever you like. Okay, so in fact, this limiting guy is precisely stationary, you know, minimal surface in this generalized sense. And notice that here is the integral means the density of this guy is, you know, almost everywhere integer, which is not trivial at all, in fact, because of the definition. You know, this guy, you know, by the way, so notice that this is not, this varifold is not rectifiable at all, because not, you know, it is kind of diffused surface energy, which is not contained on the n-1 dimensional set at all, right? It is like really making this kind of very fuzzy transition. So this measure is kind of like, well, if it's concentrated on a sort of thin region, but still not certainly rectifiable. Rectifiable means it has to be, this measure has to live on this n-1 dimensional subset, right? But so this is not even not rectifiable varifold, but the limit is in fact rectifiable and integer multiplicity varifold. Okay, so that's somehow very non-trivial result. And let's see. Any questions at this point? Fine. Just yes.
When you define it, you have a natural thing how to orientate it, because you go from phase 0 to 1.
Yeah.
Did you consider to take
orientation?
currents?
Yes, actually, you could do that too. Yes. In fact, even though I didn't write that way in my paper, you could consider so-called oriented varifold in a natural way. And you can actually consider the convergence in that category. And you get somehow so-called oriented varifold, whose notion is due to Hutchinson from 80s. Yes, actually, you do get orientation. And also, the density has to do, well, this integer multiplicity has to do with the orientation too. I don't explain this in detail, but yes, there is more than this, in fact. I'm skipping some information in this presentation. Yeah. Okay. So I'd like to, well, maybe maybe 5 more minutes. Tomorrow I'd like to give you some kind of summary of the proof, how that goes. I think it's a very nice way of understanding the varifold. But I just want to make a comment about, let's see. So this is, you know, only critical, and it's somewhat special in that Euler-Lagrange equation equal to 0. But if it's not 0, you might wonder what happens. And I just quickly mention what can be said, in fact, and that corresponds to 4. Okay, so just a remark. So I'll explain this tomorrow, but remark is that, in fact, you can do much better than this, in fact. So this Euler-Lagrange equation, okay. So now I just told you that this is equal to 0, but suppose it's not. Okay, so let me write this this way. Okay. Remark is okay. So I talked about this is equal to 0 case, but in fact the same kind of things can be said if we make the assumption that 3 can be replaced by 3 prime, and 3 prime is that for some P bigger than n over 2, the W1P norm of this first variation is uniformly bounded, then you get similar kind of statement. Okay, so you just define the same varifold, and then you get the subsequence. Then under this more general condition of first variation bounded in Sobolev space with that exponent, then you can actually conclude that well, B0 is again integral varifold. And okay, so now, of course, it's not going to be minimal anymore because first variation is not equal to 0. But the first variation of this limiting guy is going to be absolutely continuous. Okay, and this, so that means the mean curvature exists, and the mean curvature of this limiting varifold is going to be LP, P n minus 1 over n minus p with respect to this limiting surface measure. Okay. And the point is, well, you may notice that this number is actually bigger than n minus 1, or p bigger than n over 2. Okay, so mean curvature being in the LP, L something where this is bigger than n minus 1. So it is a kind of varifold where you have, say, monotonicity formula and regularity theory, for example. Okay. So it's not important to be critical. It's actually, what this is saying is, as long as you have a control of the first variation in a suitable sense, the limit is nice varifold. Okay. So that's kind of the something you can prove. So this one I don't do it, but I'd like to explain at least the critical case, which is slightly easier to explain. Okay, thank you very much.